All right, welcome to The Explainer. Today, we are tackling a really fascinating puzzle in the world of artificial intelligence. So you've seen the headlines, right? AI models are getting bigger and bigger, with hundreds of billions of parameters. And yet, somehow, you can run some really powerful versions of these things right on your home computer. So how in the world is that possible? It's kind of like trying to fit an elephant into a shoebox. Well, the answer is this really clever technique called quantization. It's basically the secret sauce that shrinks that elephant down, making all this powerful, modern AI accessible to, well, all of us. Let's dive in and see exactly how it works.
So, what exactly is quantization? Let's go ahead and pull back the curtain on this clever little trick. Okay, so at its core, you gotta remember that an AI model is just a massive, and I mean massive, collection of numbers. Quantization takes the really precise, super detailed numbers the model starts with. We're talking 32-bit floating points that can handle all sorts of decimals, and it intelligently converts them into much simpler formats, like 8-bit or even 4-bit numbers. It's all about simplifying the language of the AI, but without making it forget what it's trying to say.
Probably the best way to wrap your head around this is to think about a high-resolution digital photo. The original file that might use a palette of, say, 16 million different colors. That's our big, high-precision model. Quantization is like a smart artist who looks at that photo and says, you know what? I bet we can make this look almost identical with just the 256 most important colors. So it creates a new, smaller, smarter palette. The final picture, it looks fantastic, but the file size is just a tiny fraction of what it was. That is exactly what quantization is doing with the model's data.
Now, this isn't just some neat little technical trick. It has huge real-world benefits for you. I mean, look at this. First, the memory usage just plummets. That's why a giant 70 billion parameter model can suddenly fit on your home GPU. Then, inference gets way faster, which means you get quicker responses from your AI. It's also more energy efficient, and it saves you money, letting you tap into state-of-the-art AI without needing a whole data center in your basement.
But look, this amazing capability didn't just appear out of thin air. It's actually the result of years and years of hardware innovation built right into the very architecture of NVIDIA's GPUs. So let's trace that road to efficiency. If you look at this timeline, you can see a really clear pattern. Each new generation of GPU, all the way from Turing to Blackwell, has gotten smarter and smarter at handling smaller numbers in its specialized hardware, the tensor cores. It really started back in 2018 with Turing supporting these simple integers. Then NPR added some more flexible formats, but the real game changer for these huge AI models, that was Ada and Hopper, which brought in FP8, that's 8-bit floating point, a format that just hits that perfect sweet spot between size and precision. And as you can see, now Blackwell is pushing that boundary to an incredible 4-bit. This table really highlights that progression. So Turing and cards like the RTX 20 series, it laid the groundwork. Then Ampere with the RTX 30 series, it refined it. But the revolution, really, for modern AI, came with Ada Lovelace and Hopper. They introduced hardware-accelerated FP8 using a brand new piece of tech called the Transformer Engine, which is basically like a smart traffic cop that dynamically switches between number formats on the fly to get the max speed without losing accuracy. And this slide right here brilliantly illustrates their strategy. With the 2022 architectures, NVIDIA did something really smart. For us, the consumers and developers, they gave us Ada Lovelace in cards like the RTX 4090, which put all this powerful FP8 capability right on our desktops. At the very same time, the Hopper architecture, in those big data center chips like the H100, was built to maximize that exact same technology for huge industrial-scale workloads, tripling the performance over what came before it. Okay, so this whole journey of shrinking precision, it reaches its most dramatic point yet with the very latest architecture, Blackwell. And this is where things get really wild. Get ready for this number. I mean, really let it sink in. At a recent conference, a system with just 8 Blackwell GPUs ran a massive 671 billion parameter model, and it hit over 30,000 tokens per second. That level of performance is absolutely staggering, and it's all made possible by the next big leap in quantization. So how does Blackwell pull this off? Well, as you can see, it's a combination of a few new technologies. But the key innovation is hardware that's built specifically from the ground up to handle these new ultra-small 4-bit and 6-bit numbers. This new 4-bit format, NVFP4, effectively doubles the performance over the last generation. And it does this using a really clever technique called microscaling, which is just a smarter way to manage the range of numbers so the AI doesn't get confused by this simplification. And here's the most incredible part of this whole thing. You would expect that if you're simplifying this much, you gotta be hurting the AI's performance, right? It has to get dumber. But nope. NVIDIA is claiming that with these new scaling techniques, this move to an ultra-efficient 4-bit format results in less than 1% loss in accuracy. Think about that. You get double the speed for essentially the exact same quality. That's the holy grail. So let's bring this all together. What does this incredible journey from 32-bit all the way down to 4-bit really truly mean for you and for the future of AI? At the end of the day, it's about so much more than just numbers on a chart. This constant technological evolution, this relentless push for more and more efficiency, that is the engine that's making it possible to run tomorrow's impossibly large AI models on today's hardware. It's what closes that gap between some wild idea in a research paper and a tool that you can actually use. And all of this leaves us with a really fascinating question to chew on. We've just seen how hardware innovation made today's giant models feel small. So what comes next? What impossibly large, maybe even trillion-parameter models are being designed right now, just waiting for the hardware of tomorrow to finally run them? The race for efficiency is definitely not over. Thanks for watching.